it is a good morning, right? But I'm always have some trepidation about some of that, whether we say it's good morning or just morning, right? Because sometimes it's just morning, it's not good. All right, so this morning we have bonus presenter with Galen, Alderson, and myself, Larry Pesci. So you get twice the fun this morning, right? This is going to be great. Galen and I have presented the Vapor Trail presentation on the world's first FM radio data exfiltration tool once before, but for a limited audience at the DEF CON Demo Labs. It was probably 50 people that saw it. We talked about it a little bit on the Security Weekly podcast, so huge audience, and then probably ignored by everyone. So thank you so much for showing up, and especially first in the beginning of the conference. And, we all know that it's kind of hard to get up this early. I mean, I didn't want to get up this morning. Galen went and worked on slides because the intern goes and works on slides. And I went to the bar, so yeah. I didn't work on slides. I worked on something else, like wheat smoothies, right? All right, so let's talk to you guys about Vapor Trail and the FM radio tool. You finally got the wheat smoothies joke, right? Awesome. All right, so who are we? All right, so my name is Larry Pesci. I'm the author of the SANS SEC 617 wireless course. I'm the director of research at InGuardians, which is lots of fun. I'm also a senior managing security consultant at InGuardians. So not only do I have a management job, I actually have to do like technical work. Like that's kind of fun. I don't know which I'd rather do some of these days, but I get to look at pretty pictures, right, and charts because I'm management now. Yeah, there's a joke there somewhere. I'm also one of the co-hosts of Paul's Security Weekly. My good friend Paul Asadorian and I founded what used to be Paul.com Security Weekly, and now I owe Paul $5 for saying Paul.com, shit in my hometown. So yeah, don't say that. So we've rebranded. It's Paul's Security Weekly. We do a weekly security podcast. We've been doing this. We're pushing, oh God, 540 something episodes, 52 episodes a year. We're pushing 11 years of a podcast. Woo! Damn, yes sir.
What does G-Unit Studios look like?
What does G-Unit Studios look like? Just like you imagine.
Nice. So
if you see it on camera, yeah, when you see it on camera for G-Unit Studios, it's exactly what it looks like. Yes, there's a 55-gallon drum of lube in the back step, and yeah, there are, so it's been interesting for the evolution of the show. I won't go too far into it, just because it's like totally off the rails. But, we started recording the podcast almost 11 years ago in any location we could find, which was often an unused conference room in a local university where Paul worked. And then we would move into the conference room in the healthcare organization where I worked when it wasn't used after hours and stuff. And we were literally assembling and disassembling the set and the audio equipment every week, and it was awful. We finally ended up in Paul's basement at his pool table, and then they sold the pool table, so we moved into his actual office, and now we rent two offices in a strip mall, like side by side. We started with one, we did everything there, and then the barber shop next door went out of business. So we cut a hole through the wall, and now we have one side for just the set and one side for production and pizza. It's fun. It's amazing how far you go in 11 years. So, all right, so I've also done a lot of hardware tinkering in many cases on the show. We've showed up at the show, and Paul said, "Hey, check out this new thing I just bought," like literally still in the box. And he will turn around, and my Leatherman is out, and I've got it half disassembled before he's even plugged it in and turned it on. That's what I do. I book inside of stuff. So I play with hardware a lot, and lots of fun. I also have my amateur radio license. I'm an extra class operator. The call sign of KB1 TNF, the one assigned to me by the FCC. I didn't go for a vanity one, just because I thought, it's kind of neat. And my dad had one that was signed to him by the FCC as well. And he used to come up with this mnemonic to remember his own call sign. And of course, it's Whiskey Bravo, and so forth, using the NATO alphabet. So mine would be Kilo Bravo 1 Tango November Foxtrot. But for me to remember it, it's Kevin Bacon 1, that's not funny. Right? Yes. All right. So, animations. All right, and then we have my wonderful intern, my super kick-ass intern, Galen Alderson. He's really new at this. You know, Galen's 19, just out of high school, decided not to go to college and come be an intern for us. And it is, yeah, right? I mean, what do you think, whether you go to college or not, that's a decision. That's another one. He's not a stranger to this industry. His dad is one of the founders of InGuardians and has been present in all of this security stuff just by osmosis because his dad has been in the industry forever and he's been experienced to that at home.
Yep. I remember 8 years old watching him run Nmap scans. He told me, if anything pops up here, run and tell me.
And you ran and told him often.
Yep.
So this is his first real security presentation. He's done other stuff in other industries. I'm humbled by the intern in that sometimes the student becomes the master. And for me, I wish I was where Galen was when I was 19 type of thing, as in super smart guy, and he's incredibly well-rounded for being 19 years old, and part of the reason why we hired him. And hopefully he sticks around with us for quite some time. So, no stranger to the industry, and he's got a lot of stuff under his belt. All right, so enough about us. Let's talk about Vapor Trail, right? So, being the director of research in Guardians is a really interesting place in that I get to spend some time with one of the founders, Bob Hillary, and as we put it, we have a meeting once a week, Bob and I, that we label on our calendars. It's called the X-Files. And it's because the truth is out there somewhere, but we have no idea what the truth is. And what do? We talk about crazy ideas. We literally spend an hour on the phone together once a week and talk about crazy stuff. What if? You know, what if, like, what's the gentleman that wrote some of the new books on some of the digital hacking futuristic stuff? Name is escaping me at the moment. Figures. But the last one, what's that?
Strauss?
No, he's. Let's make it like even more obscure, right? Like, who's that guy that writes the digital security book things? Yeah. He did some recently. The big one was that they were Change Agent was his latest one. Change Agent was interesting in that they, what's that? Daniel Suarez, thank you, sir. And Bob and I had read his latest book on Change Agent, where they talked about doing genetic modification via CRISPR, being able to modify DNA on animals and humans and stuff to get the proper output that you want. So change the input to get the proper output. And it was really interesting. And then, like, man, that's crazy. Like, Dan's like sort of a futurist, and he talks about this type of stuff. And we saw that just the other day that scientists have taken pigs and made them low fat. Like, literally, like using CRISPR to modify their DNA so that they can have a low fat pig. Like, what? Why would they do that? Oh, apparently there's this whole magic about how fat or how lean your pig is as to how it develops, and it's amazing. So we talk about like CRISPR, like how can we develop CRISPR stuff for IT security? And one of the things that Bob and I ended up talking about was some of our guys were having some problems one day with an on-site with a customer, and they wanted to do data exfiltration. And every time they started doing data exfil, they got caught. No matter what they did HTTPS, HTTP, they started, like trying to tunnel stuff over GitHub commits, and they were getting caught every time. And I said, there's got to be a better way. Bob, what can we do? And we were looking at some, Galen and I were practicing, and we were getting Galen up to speed on some stuff, and we're looking at some software-defined radio. And Galen had rewritten some software applications to do radio transmission on the Raspberry Pi. And I said, well, if we can do FM radio transmissions on the Raspberry Pi with a piece of wire and a $35 computer, if we can do FM radio transmission and it's got an Ethernet port, what happens if we can plug this into somebody's network and get data out that way? Huh. So how do we do that? It was one of those, we're talking about making low-fat pigs, and this thing just crazy comes up about being able to exfiltrate data over FM radio. We thought, well, let's see what we can do. The big one was that we had a problem. Our guys were on site, they couldn't get data out of a network, they wanted to get data out of the network. How can we enable them when they have physical access to that network to be able to plug in a jump box of some variety or a drop box, and they've got access to the network. Now they need to get that out. Well, there were a couple of problems that they were having, and there's a couple of problems that we saw as well. Ooh, animation. So our solution was FM radio. Why? Well, if we think about the traditional exfil methods that we see a lot, you go and plug a Dropbox in someone's network, either for good or for bad. How do you get the data out of the network? Well, you either send it back out their own network through their firewall where they can inspect the traffic. They can inspect the traffic, they can do SSL termination, and then decrypt it and inspect all of that traffic as well. So folks have a really good ability in properly configured networks, and folks that are doing a really great job can see that traffic outbound on their own network. Well, that was the problem we were having. Some of the things that we're thinking about is, well, let's just send it over cellular. Well, all right, then that becomes potentially encumbered in that we have to have a cellular modem of some variety, and we have to have a SIM card that's prepaid, and if you don't use it for 3 months, they take all the funds away, and it just becomes ridiculous. There's also some potential for actually doing detection with cellular stuff, and that folks are getting much better at doing detection for cellular type of stuff. We thought Bluetooth, and well, Bluetooth range is not that great, and it's fairly complex, and Bluetooth low energy, and that's not secure. We thought about a lot of stuff. And then we wanted to make it accessible to everyone with cheap hardware. And doing FM radio on the Pi was great. Because think about this. How many organizations do you know of that are doing inspection of traffic over their network wired based out to the internet? Lots of them. How many folks are doing inspection for Wi-Fi? Detecting rogue access points, detecting new clients on their networks? Yeah, probably quite a few. Maybe not as great at it, but getting better. How many folks in organizations are doing detection for cellular stuff? Not as many, but in our opinion, we had some other encumbering issues. How many people are doing Bluetooth detection? Not many, but getting better. How many people are trying to do detection of rogue signals over FM radio in an organization? I can think of one organization that may in fact be doing that. It's a 3-letter government agency that doesn't exist because there's no such agency. You know, those type of people. Yeah. So who's detecting this stuff? No one. This sounds like a great avenue, right, to get data out of our networks. All right. So what did we do? We wanted to be able to hide in plain sight with some traditional FM radio stuff. Doesn't require a special license for us to transmit because here in the US we have the ability as consumers to be able to transmit in the licensed FM band, without a license at low power, under I think it's half a watt. If you think about that, it's very much when we used to have our sewing Discman in our car and you didn't want to have the little cassette adapter thing, you would actually pick up some stuff that actually did a little FM transmitter in your car so you could turn your radio to like 101.3 and would receive the audio from the Discman. And like, if I think about going home right now, that's exactly how my satellite radio transmits to my 2003 truck. Like, no cassette FM radio. So we are allowed to do low power FM radio. Cool. We had some challenges. We went and looked at all of the ham radio digital modes for doing digital transfers. And while we took some inspiration from some of those digital modes, they weren't going to work for the platform we chose. And Galen's going to talk about why some of that is very shortly here. we wanted some inexpensive hardware. We went with the Raspberry Pi and a length of wire. I mean, wire is free, right? Because there's how much wire is in this room that we can steal to make antennas, right? Lots. Like you can go on the street and find wire laying in the street. The Raspberry Pi and the SD card was really the big expense to be able to do transmission. And then we can receive with just about any software-defined radio. Galen's actually going to do a demo for us with a $35 kit for the RTL-SDR, an inexpensive software-defined radio receive only. And it's the high-end kit because it's got an aluminum enclosure and it comes with a bunch of antennas. So you can get them for $5 if you order them from China and you get the really crappy antenna. But we picked the high-end one because they work really well. So we need one device for transmit, which is the Pi, which has Ethernet, meaning we can plug it into someone's network and gather data, and then we can transmit it with a piece of wire on the Raspberry Pi. It is possible, and Galen was attempting to work on some of it last night, future considerations, so to speak. It is possible in the current state to take another Raspberry Pi and plug an RTL-SDR and a length of wire into it on the same device and have it both transmit and receive to create a repeater so we can increase our distance. And because it's a Raspberry Pi, low power draw, we can run that off of a battery. So one of those nice little USB battery things. So fun stuff. So we can effectively extend our range. All right, so ultimately, how does it work? Well, we go into an environment where we want to exfil data from. And we fire up our software-defined radio or radio in our car and look for an unused FM broadcast channel. Like, where's not something broadcast? We pick that, and then we configure Vapor Trail to use our frequency that is unused, which is easy to do because Galen did a great job. You don't even need to power on the Pi to make it happen. You take the SD card out, you plug it into your machine, and it's on the boot volume, which is a Windows FAT32 formatted file system. So you can change the frequency without even having to boot up the Pi or access it, just right into your machine. We find some network tool that we can use to gather info from the victim network. Our initial intent was for us to use Responder so that we could capture hashes over the network and then exfiltrate hashes so that we could reuse or crack hashes to get access to the VPN. But that's good. And small bits of data. So find some tool that we can use to gather data from the network that we can use to exfil. And then we can have Vapor Trail monitor those directories and do some exfil. We initially thought about adding some automatic compression to that. We decided not to, but we can leave that to a shell script with something like gzip or something like. We then use Vapor Trail to encode some our acquired data into a specific format, and then use RPiTX. RPiTX is one of the tools that was developed for folks to be able to do FM radio audio data stuff over with the Raspberry Pi by toggling a GPIO pin to create FM signals. The big one was the first exposure I saw on this was Make Magazine. Make Magazine said, make your own radio station so you can take your music to the beach with your Raspberry Pi and put your music library on a Pi, and then you can create an FM transmitter so that you can listen to your music at the beach. Like, I don't bring Pis to the beach. Have you seen me? I have TV tan. Right? I don't go outside. But I'm like, well, all right, if we can toggle a GPIO pin to create an FM broadcast station, well, that might be interesting. So leveraging standing on the shoulders of giants, so to speak, in that we're leveraging some other really great work that folks discovered you could toggle that GPIO pin to create FM signal. Let's use their tools to make that happen. Great. Some other things that we needed to consider was the Raspberry Pi is not a terribly robust platform for doing some of this stuff, very prone to error, which Galen will explain some of the things that we need to fix that with our custom digital mode. The big thing is that we should probably consider transmitting this stuff multiple times because we are doing transmit from the Pi, receive only on our destination. There's no ability for us to call for retransmission because it's a one-way communication. So if we miss something, it's gone. But if we transmit multiple times of the same data, there's a possibility that somewhere in there we'll get all the data and be able to reassemble it. All right, now the fun stuff. All right, so Galen, you're up for.
All right.
So Galen's the one that designed our custom digital mode, and I'll let him explain a lot about what actually happens with a digital mode.
Right. So Vapor Trail is kind of, the tool has two layers to it, and the first one is the actual digital mode, and that's the way it transmits data over the air. And I'm actually going to use a different slide for that.
This one?
Yes.
Yay!
So this is frequency over time, and this is kind of similar to what you might see in the waterfall display of a tool like GQRX. And so it's 1 bit per, we have a signal which is oscillating between left of a center frequency and right of a center frequency. And depending on how far away it goes from that center frequency, that indicates the value of a bit. So the ones near the edge of this image here are 1s, the ones near closer to the middle are 0s. And it doesn't matter which side it's on because, yes. And signals on either side of the center frequency are still 1s and 0s. It's just based on that distance. And then what indicates the end of a bit is when it crosses that center frequency. What that means is that it can spend as long as it wants on one side of that frequency, and it will still be a valid bit. And that solves the one major challenge of the Raspberry Pi is we can't make timing precise. Because the Raspberry Pi is manually telling the oscillator to change frequencies. And while it's doing that, Linux is also saying, hey, I want to do stuff, I want to schedule tasks, so stop, and it's also reading from disk. So sometimes it's not perfect on the timing for those transmissions.
Yeah. For example, we were working on doing some, the pager challenge that we've got going at the booth shortly after this presentation. And by doing the transmit of pager data with the GPIO pin, when I SSH'd to the Raspberry Pi that was doing that data, and pager data is very time sensitive, you could literally hear the pager data going specific frequency and data rate. You could actually hear it. And then when I would SSH to it, and when it did the initial SSH key exchange, you could hear when it was done. You could hear it change pitch and speed, which of course for pager data was horrible because it was very timing dependent. And that was some of the things that Galen was dealing with, was on the timing, is that the timing could be way off. So he decided to do the bits based on the cross of the center frequency. So it could spend as long as it wanted on one time, and it would still indicate the same bit.
And this was after a few weeks of struggling with the other more timing sensitive modes, trying to get them to work and not having much success. So then the other part is great, you have a way to transfer bits. How do you actually, send bytes and get data that you can actually read? And so the way that works is data is read in by the Vapor Trail tool and chunked up into 128 byte blocks. And it will collect 16 of these blocks and then generate 16 parity blocks and transmit all of those 32 blocks. Now on the receiving end, as long as you get 16 of those blocks successfully, you can recover your original data. It doesn't matter which 16 blocks. So you only need to be able to read half of your data, which helps because despite making up for some of the errors of the Raspberry Pi, there's still transmission errors due to the signal being a bit noisy and the decoder being a bit early alpha quality. So
very similar to if you've ever downloaded anything from a binary news group, because everybody does that. Nobody's ever downloaded material from a binary news group. And if you've ever done that, they will often include what's called PAR files. They're recovery blocks, so that we can, if you miss one of the blocks from the binary news group or one of the postings, you can potentially reconstruct that block from the PAR data. So the recovery blocks can reconstitute data that you have been missing. So we used a very similar type of thing with Vapor Trail using ZFAC.
Right. So as a result, the minimum transmission size is 2048 bytes. So if you're encoding a message smaller than that, it will be padded out with zeros to 2048 bytes to fit within one of those blocks. What else?
What were you doing last night? Why were you reviewing these slides?
Right? Yeah. Sorry.
So some of that with
Take that for a moment.
with the Raspberry Pi, we can have some frequency drift as well. And as part of the tool that Galen wrote, he has the ability to do frequency detection based on a little bit of drift, just because temperature and all of that type of stuff, and volume and you name it. We were working on some stuff yesterday, and really robust in that it can actually figure out where the signal needs to be.
Yeah. And so it can make sure that the data is correct because there's a bit of overhead. It adds a checksum to each of these blocks. Otherwise, it might just be garbage data and you wouldn't know. But the checksum adds a bit of data. It's a SHA-256 sum. And so with the larger block size, that checksum overhead would be reduced, but you'd also have higher latency because you would need more data before you could transmit anything.
Yeah. So unfortunately, there's lots of overhead.
Yes.
There's lots of overhead because we're using really crappy hardware that's subject to all sorts of issues based on timing and the environment, and we're using a really crappy transmitter because it's cheap and we want to make it accessible to everybody. So there are lots of things that Galen had to do to overcome all of that. Unfortunately, that means lots of overhead.
But you can make up for a lot of that by compressing your data, because if you have very compressible data, just compress it before sending it, because this is not limited to just text data. It's any sort of binary, bits and bytes, whatever you want.
Right.
One of the issues right now, and something I want to work on when I actually have time, is he mentioned being able to transmit multiple times, listen in, and reconstruct from that. That's not something it can do right now because it doesn't have any way to link multiple transmissions together and know that they're the same data. And that's something we'd have to add in the future. But that builds on top of the transmission protocol because the transmission protocol can stay as it is and just send data however you want. And then you can build whatever you want on top of that because you can send whatever you want. So you could send some sort of identifier saying this is this block from this file, and if you get it again, put it here.
Yep. So it's a fairly easy expansion thinking about that.
Exactly.
Right now we're only identifying blocks by block number, but not identifying a block number per file or transmission set. So that would be a fairly easy expansion to do with minimal overhead.
Right. As for the data rate itself, it transmits, our demo is going to be at 2,000 bits per second. That's 2,000 bits per second including overhead, right? That's not 2,000 bits per second. You can't just take your original data, divide it by 2,000 bits per second and get how long it's going to take. You're going to have to take your original data, account for doubling the size because of the parity, and then account for the overhead of the checksums.
Yep. So it's not terribly speedy, but if you're sending hashes from a responder, who cares? It's small amounts of data that you can wait a little bit for, because in my opinion, the value of that data, it's worth the wait. That saying, good things come to those who wait. Yeah, wait.
And if you know how to filter out what you want ahead of time, well, you're just running Linux, so you can use any tool you want to say, hey, I have all this responder traffic or something, and I want only these parts, and then only transmit those parts, so you're not wasting time transmitting data you don't need in the first place.
Right, what's the joke that, right, I have too much data, so I have a problem, so now I'm going to use sed, awk, and grep, and now I have two problems. Right? Sed, awk, and grep is the second problem. Right, so yeah, you can filter the data that you want prior to transmission using command line kung fu.
Yes.
Yep. So Galen Haskell, really?
Right. So that's the language I'm most comfortable with at the moment, and I needed to write something, and I needed to write it quick, so I went for that. And it worked. But there's a downside, and that is there is no Haskell compiler for ARMv6. The Raspberry Pi B Plus and the 0 are ARMv6 processors. The 2 and 3 are ARMv7, so it runs just fine there. But I'm going to need to rewrite the encoder step to run on ARMv6 if we want to get it running on a Raspberry Pi 0. However, we have done tests with the Raspberry Pi 0, encoding elsewhere, putting a file on there and transmitting, and it can transmit just fine. We just need to get the encoder running on that hardware.
Yeah, so buy the more expensive Raspberry Pis, right? Not the $5 one, the $25 or $30 Sorry, guys. But
The upside is you get more processing power for your filtering, so hey.
yeah. All right, so we've seen these slides, the crossing mean zero, right? All right. So we've got some really great stuff, and Galen's going to give us a demo of it momentarily here. But of course, you come up with a crazy idea, and you implement crazy idea. What's next for said crazy idea? And we've thought about a lot of crazy ideas, and some of these are really, really crazy. We talked about potentially porting some of this to other platforms. So like one of the Raspberry Pi clones, the Orange Pi, like even cheaper Pi-like hardware out of China with additional feature set and all sorts of craziness. We talked about putting this on Windows 10 IoT. Why? Just because. Like, who actually uses Windows 10 IoT stuff? Exactly. All right, so maybe we should cross that off the list, right? Because we're using pulse width modulation to toggle a GPIO pin, and a lot of the fan control on modern motherboards to do the fan speed is via PWM. We were wondering if we could make an application for something like Windows that could toggle the fan speed to transmit FM data with the fan PWM control. Like, this is like the totally crazy, like, instead of needing a Raspberry Pi, you just run an app on a computer that you compromise. Like, ooh. Well, yeah, that one's a little bit out there, and maybe
Back to X-Files territory.
Yeah, back to X-Files territory. Some other things we talked about was some custom hardware for better FM transmission, because toggling a GPIO pin to do FM transmission, or any transmission for that matter, is, pardon my French, fucking awful. It bleeds over to all over the entire spectrum. It's a square wave. It's dirty, but it works. We could make this better. Some other things that we've talked about to be able to maybe create a custom shield so that we can do both transmit and receive on the same device at low cost. So my thoughts were, well, toggling GPIO pin, great. Maybe we can do an FM transmitter, a real FM transmitter, and some sort of receive on the same board with like re-implementing an RTL-SDR chipset with that tuner on a shield, so you don't have to plug in USB and have one device that you can plug in and do transmit or receive. Getting it.
Yep.
We're using a piece of wire for an antenna. Maybe we can do an on-PC board antenna. We've discussed fractal-based antennas just because fractals, and they're kind of cool looking. We've talked about some possibility for encryption, and then thinking about the possibility for encryption is we're doing this from the Unix command line. You guys have heard of PGP, right? And all this stuff. Yeah, why can't we pre-encrypt the data prior to that, as opposed to having to do key negotiation over the air? Because currently it's a one-way transmission. How do you do one-way key negotiation? Yeah, like we need to get with Diffie and folks back on some really drugs back in the 60s, and come up with Diffie-Hellman variants again. Some other ones from Galen. He's thinking about doing some different implementations as opposed to Haskell.
Yep.
Because trying to build some of the stuff in Haskell build environment is considerable.
And so talking about the idea for a shield, we were testing earlier with an FM transmitter, a little FM transmitter chip, I2C controlled.
The future.
Oh, is this over here? Oh, well then I'll talk about it here.
The future.
Yeah. So we were testing with this. It has some problems because it makes the transmission consistent with timing, but we already established that we already accounted for inconsistencies with timing, and it introduces other inconsistencies that make the transmission sound fine but not work. So if that's going to be a thing, we need to look at that more.
Yeah. So we were literally out in the other room yesterday, spending some time doing transmits between our PyTX and the actual FM transmitter module with the KT Micro KT0803K on it. Which of course is I2C control from the Pi, which we used to set channel and gain and all that stuff. And all of the drivers out there were available for the Arduino. So Galen wrote a set of drivers for the Raspberry Pi, which are available out there for anybody who wants to use it. And that's what we're using to control said radio chip to do actual real good FM radio transmission. The problem is that it now requires audio input to the FM transmitter board, which means we have to use the FM the audio output on the Pi as opposed to just pulling it from the board itself with the toggling GPIO. So now we add another cable.
Yep.
And there's no pinout for the audio on the Raspberry Pi breakout connector, which sucks. So maybe there's some options for remapping some of those pins at some point, but we haven't gotten that far.
The good news for non-vapor trail projects, though, is that if you have something that's timing sensitive, this makes it work a lot better. So Larry is doing some pager traffic transmission, and that went from sometimes decodes to most of the time decodes.
Yes, great. So great improvement. So as part of the booth next door, where the mules and all the vendors and stuff are, we do have a booth. We have a little challenge going on for being able to decode pager data legally, I might add, because I'm giving you guys permission to do so. And we're actually using the KT Micro hardware to do that transmission because it is very timing sensitive. We're using that as like the beta, alpha, gamma test of the hardware for VaporTrail to make some of this happen. So you guys get to be our guinea pigs and see how well it's actually working for this. So this way, it worked at my house. It worked the other day when Galen tested it. So you guys get to help us out with some of that, and we really appreciate it. So we are giving away prizes for those who finish the challenge. So the challenge is decode some pager data. We give you an idea where it is. There's some conversations that happen. Answer some questions about the conversation. There's a bonus question. Bonus question wins you booby prizes. The other questions get you the opportunity to enter a raffle, and we're giving away a USB killer. You guys seen these things? Oh, yes. Yeah, we have the real USB killer with all of the added connectors and all of the stuff and the test shield, so you can test it without actually killing devices. So yeah, we're giving away one of those to folks that actually complete the challenge at random draw. So fun stuff.
So another idea for the future, if any of you have seen the POC or GTFO book, there is a section about ARP-ITX, and one of the ideas that it presents is to put a bandpass filter after the GPIO pin to limit how much frequency noise is generated by the transmissions. Limit it to only the area you want to transmit in, rather than all the other parts of the frequency range that it happens to transmit a little bit anyhow.
Right.
Yeah.
I was wondering, what is that baseband frequency? Is it already in the 1700 megahertz range, or are you stepping it up?
So the Raspberry Pi has a very large range from, I think, the hundreds of kilohertz to the hundreds of megahertz in terms of what frequencies it can reach with that FM transmission.
Yeah, and it's all dependent on how fast you can toggle that GPIO.
The way it works is actually, it's not being toggled on and off by like a user space process. The processor actually has a feature for pulse width modulation built into it. And you can tell it, hey, go toggle that pin at this frequency. It'll go do it for you. Now you're done. What you have to do is then tell it when to switch frequencies. But yeah, so if we were to build a shield of some sort with an antenna, we could include a bandpass filter on there. And if that filter's frequency was controllable by the pins, then we could make it much nicer to all of the neighbors spectrally.
Right, because right now it's awful to all the neighbors. Really awful. All right, so what's next?
Is it demo time?
All right. Martin, one moment, we're going to switch computers here because the demo works really well on Galen stuff and not mine.
Ooh, that's hot. Well then, let me switch resolutions real quick.
And this is where the chicken sacrifice.
There we go. All right.
Oh, wait for it.
We're good.
There we go.
Oh,
all right.
Perfect.
So Galen's got GQRX, free open source tool for tuning with the RTL-SDR and looking at waterfall display. So on the top, FFT graph, bottom, waterfall display. So signal in real time on the top, the FFT, and signal over time in the waterfall display. And he's currently tuned to 97.7 megahertz, which is in the FM broadcast range.
Right. So I may have mentioned earlier that transmitting and decoding especially is a rather manual process right now, which is another thing that I'm hopefully going to fix as soon as I have time to do it. So the first thing, so this is GQRX. Down here is a button that says UDP. When this is enabled, it's going to just send data to a UDP port, and that's the data after the FM demodulation. So if you were to tune in to, say, a radio station, then the UDP data is the actual audio that you'd be hearing.
Yep.
So we're going to come over here and run a script which will start listening for that data.
Yep. So it starts up SOCAT, listening on the default GQRX UDP transmission port, listening for UDP packets, and then writes it to a file.
Yes. And these scripts are available on the GitHub repository as well for Vapor Trail. So over here, we have a transmit script. And what we're going to do is just...
Yep, so the first one was local to Galen's Mac, the receive script. He's now using a serial connection to the Raspberry Pi to kick off a transmit on the Raspberry Pi with a piece of wire attached to it.
Yes, so this is actually running on the Raspberry Pi. And I'm going to send this to the transmit script. What this will do is encode the data, and then after that's encoded, it'll hand it off to our PyTX to transmit it. And we can see that happen by watching the waterfall display.
Yay.
If I zoom in here to make it nicer to see. So what you can see here is you can see 4 distinct peaks. You can see peak over here, peak here, peak here, peak here, and that is what I was mentioning in the graphical slide earlier. The 2 inner peaks are the zeros, the 2 outer peaks are the ones. So hopefully, if that transmitted good, then we'll have some text. There we go.
Those poor chickens lost their lives.
Now it took a little bit,
Yeah, so
but
it took a little bit.
that's because it was padding that data out to 2048 bytes.
Right. And Galen mentioned that this is not just for text. We can do any sort of binary data that you want. And of course, I may be setting Galen up for failure on this one.
Now this one stresses it a little bit more because this one uses 2 of the groups of parity chunks that I mentioned before. So it's very possible that we get a half-formed file here.
So Galen, what does the PNG look like before you send it?
I'm sorry?
So what does the PNG look like now before you send it?
Like the data sum?
Yeah, no. What does it
Oh.
look like visually?
Well, I don't have it.
Picture of?
I don't have it on here. I have to send it first, of course.
Smart. See what I mean about the intern sometimes being smarter than the yeah.
But I've printed out the SHA-256 sum here. So if this matches, then we know we got it right. If it doesn't, we know we got it wrong. So let's start this receiving and tell it to dump to a file. This one should take twice as long because it will be using 2 of those super blocks.
Yeah. So it hasn't started transmitting yet because it is still taking the larger amount of data and then encoding it into a format that actually can be transmitted. So again, this one takes a lot longer. There is a lot more data. The initial one, because it was short, it had to get padded to the full block size. This one with the PNG actually consumes enough data that it requires 2 full blocks to be transmitted. So again, twice the amount of time. So bear with us for a little bit. This is actually real time in the air sending this stuff.
Yes. Now one question I have is if this port has audio output, because I may be able to give you a second of that. I don't know if I could bear much more. But
it still sounds pretty neat.
Why don't we try? We'll try it in a moment.
Oh, I finished.
So let's see. So now we're done. We'll hit enter.
Wait for it.
And you'll notice this won't print anything out because we've told all the output to go to this file. So if we check the sum, that matches. So we got a successful encode. Open this image. I've killed the computer.
And it's a really small image of the pony that this was named after, Vapor Trail. Now, this is a really small image because we actually wanted this to actually finish transmitting while
Yes.
you guys are sitting here and not have to be standing. All right, what does this look like? Come on now.
It is actually almost 6,000 bytes.
Yep, but it works, and it was binary data for an image instead. So So Galen, can you have him at least see if we can see what it sounds like?
Yeah. And to do that, I'm actually going to send the receive script, because I can do that. Actually, just for fun, I'm going to show you that we can do encryption. Or not encryption, sorry, compression. So here's our receive script. We're going to send that through gzip and then send that to the transmitter. And on the receive side, we just do the opposite. We do receive, send it through gzip with decompress, and go.
Untested. He's doing this on the fly.
So let's see if we get any sound over here. Oh, it's on my, I'll turn it up. So that's what it sounds like. I don't know if you could hear that from over there.
Yeah, you don't want to listen to it for too much longer. Yeah. But for me anyways, listening to that is a really great way to do some of the identification of some of those transmissions. Like I can listen to POC pager traffic and know wherever I've tuned to in some band, I'm like, that's pager data. Because I've heard it multiple times. So
here we go. We've received it, and it went through gzip to actually decompress that data. And if you have a large amount of data which has a lot of repetition, which you'll find in log files, then this can be a massive help.
Yeah.
And also, because of how slow this data rate is, you will not run into problems. Like you can use the maximum compression, and it will still be transmitting so slowly that it doesn't matter, because the transmission time is going to outweigh that significantly.
All set?
Yes. Boom.
Trevor.
We should have had an image of Trevor.
I know we should have. Sorry. All right. So, demo. It worked. So that's it. We're actually doing pretty good on time. If anybody has any questions, I think we have a couple minutes or so to do so. Other than that, we'll give you the opportunity to ask some questions, put some contact info up, and some places where you guys can get the tool. Yes, sir.
Yeah, you said half a watt for the broadcasting. What's the effective range look like that clear site, and then say like in a building like this?
Sure. So our testing hasn't been very empirical. It's been in our stuff. Although we have had some folks use RPITX that have talked to us to like set up a little pirate radio station type thing. And they were in a very urban area, I want to say downtown San Francisco, and they were able to cover about 3 city blocks.
Wow.
Yeah.
Way further than I thought.
Yeah, way further than
Yep.
I thought too.
Line of sight definitely helps.
Yes. Yeah. And that said, they were fairly high up, but so 3 city blocks. Estimating at 300 yards is probably a good estimation, I think, without line of sight. But that said, we can build repeaters
Yep.
fairly inexpensively to capture that and then potentially retransmit on yet another frequency to get additional distance.
And I've
build
sorry.
those on the cheap for like under $50.
Yeah. And I've transmitted through multiple walls, although the distance between those walls is a little bit shorter, but it definitely goes through walls pretty fine. And the great thing is you can use just a massive antenna. Now your reception's better, because since it's one way, you have the advantage that it doesn't need to be able to receive data out the other end, which is a good thing and a bad thing.
Yeah. Any other questions? Yes, sir.
Have you tried going out beyond the normal FM broadcast? I know it's illegal, but if you're doing this, you're not legal anyway.
Right. Well, actually, we could be conceivably legal. I mean, we could be doing an authorized pen test and exfilling data that way using the low power output. And absolutely, we have done tests in the 2-meter ham radio range. And part of that is why I have my ham radio license. We just, as part of the ham radio transmission in those ham radio licensed bands, we have to be able to identify the transmission with the ham radio call sign. They don't say how you have to do that. You can put Wi-Fi in ham radio bands and do that, and you need to identify your transmission. Well, you can identify your transmission by creating the SSID of your wireless network being your ham radio call sign. We could label some part of the block with my ham radio call sign. So we could definitely expand it to do some of that as well.
Potentially get some more range.
Absolutely, you could potentially get more range. We could also use different transmitters to get in those ranges as well.
I was going to say,
Yes, sir.
those cheap ball things off of Amazon.
Yes, buy a cheap Baofeng radio and have the automatic detection for something like PTT. I mean, those Baofeng radios are what, $35? Yes, so absolutely something you could adapt to something like that. And in fact, I have my Baofeng radio with me.
I've got one if you want.
I've got one too. So it's in the bag right here. So that might be something interesting to play with. So now do I dare kill my programming cable at this point to get the stuff we get? So any other questions? Woo! All right, thank you so much.
Thanks.